Suppose this is a common data question. Suppose the physical address are 32 bits wide. So the number of bits in a physical address of memory is 32 bits. Suppose there is a cache containing 256k words, and each cache block contains 4 words. Each word contains 4 bytes, and memory is byte addressable. So if 32 bits is the total bits used, means total number of bytes, it is 2 power 32. So memory is byte addressable. Actually, we can do like this. The question number 1 on this is, for a direct mapped cache configuration, specify how many bits are used as a tag. Usually the physical address 32 bits, we have to divide into some tag and index, usually, where index is a part of a cache and the tag is the total. Tag and index together is the physical address, that is 32 bits, and index is only used for the identification of the cache. That depends upon whether it is divided into blocks or not. So here there are 4 words. 4 words means actually each word containing 4 bytes. So the number of bits to represent a word is 2 bits. Okay, and again the block contain 4 words. So the block offset we can represent with 2 bits. That is, number of bits required to show a word is 2. The number of bits required to show a content of a block is 2 bits. So that we have to represent number of blocks also. So that depends upon the cache size. Say for example 256k is the cache size. That is 2 power 8 into 2 power 10. Total 18 bits are required to identify a cache usually. But it has been divided into blocks. How many blocks you can have? So in each block how many words are there? 4 words are there. So that this is 2 power 18, we can divide with by 4, means 2 power 2. That means, so the number of blocks will be represented with 16 bits. So the number of blocks will be 16 block, because it is a direct map. There is no associative, there is no set associative, directly it is mapped. So that it depends upon the number of blocks. So the number of blocks is 2 power 16. Okay, each block is containing how many words? 4 words. Each word is containing 4 bytes. That means the number of bits required is 2. So 2 plus 2. So total 16 plus 2 plus 2. Total we are using 20 bits for cache identification based on the blocks. And again, out of this 32, if 20 bits are over, then there is only 12 bits for the tag. Okay, this index is divided into 3 parts. One is the number of blocks, followed by block offset, content within the block, and again content particular word. Number of words is block. No, in a particular word how many bytes are there? Bytes within the word. So this will be the index. So that the index can be divided. The total number of blocks will be 2 power 16, 64k. So the 16 bits, plus in each block we are having 4 words, that is represented with 2 bits. In each word we are having 4 bytes. 4 bytes can be represented with 2 bits, because 4 can be written as 2 power 2. Total 18 are over. So out of this 32, if 18 is over, then remaining 12 can be used for the tag field. So option A is the correct option here. And there is one more question on this, that is for a two-way set associative cache configurations, specify how many bits are used as a tag. This is the second question on the same data. So here it is two-way set associative. So here there are 2 blocks for set, because it is two-way set associative. Total this 64k blocks is already we have taken 64k blocks, because 16 bits we are used. And if it is two-way set associative, this 64 is divided by 2, that is we can get around 32k. So 32k can be represented with only 15 bits. So 15 bits are required instead of 16 bits in the index field. So 15 bits, and followed by these 2 plus 2 are common. 2 for the block index, block offset, and 2 for the this thing. So again in the tag portion only we have to use an additional bit to indicate them. So only we have to use a particular content. So that 15 plus 2 plus 2 total, this 19 bits only we use So 32 minus 19, we get total 13 bits for the tag. Only thing is the 64K we have to bifurcate into two parts because it is a two-way set associative, that is 32K. We can get 15 bits only instead of the 16 bits for the block identification, as it is two-way set associative. It is divided into two sets. So the total, it will be, option will be 13 bits. 13 is the right answer, because 13 minus this 32 minus this 19 will be 13. Option B. This is a linked question. The data given is, consider the following language: L is equal to A power n, B power m, C power m and D power n, such that n comma m starts with 1. So here, so n number of A's followed by m number of B's followed by same number of C's followed by n number of A's. A's and D's are equal, B's and C's are equal here. What is the minimum yield of the above language from equivalent parse tree? Usually we find the minimum yield of a language through the parse tree from the grammar actually. Okay, so here let us suppose the solution of this will be like this. Minimum string of a language is different from minimum yield of a language. Minimum string is not always equal to minimum yield. Okay, so the grammar, equivalent grammar for this language is S2 ASD or AAD, again A2 BAC or BC. So here B's and C's can be maintained equally along with A's. Whenever you want to stop A's and D's, we take this production AAD. Whenever you continue A's and D's, then you take in the S can be replaced with ASD, otherwise S can be replaced with AAD. So for this, the equivalent parse tree will be like this. S2 will have ASD. Parse tree should cover all the productions. So again leaf node is A and D here. S should not be a leaf. Again S2 AAD can be used. We can use AAD, and again A2 BAC we can use. C is the terminal string here. Again A2 BC. So this is the parse tree. So the minimum yield is nothing but the string obtained when you read all the leaf nodes from left to right. What are the leaf nodes? A, B, B, C, C, D, D. All the leaf nodes you have to write from read from the left to right, so that you got AA, BB, CC, DD. This is the minimum yield. That means the string obtained from the parse tree, not from the, actually minimum string is ABCD here. The minimum string obtained from the grammar. But the minimum yield is nothing but the string obtained from the equivalent parse tree. So that we got this AA, BB, CC, DD. Option C is the correct option here. Option C is the correct option here. So now we have to, there is one linked question on this. So the answer of the linked question is based on the answer of the first question, that is AA, BB, CC, DD. So the question given is like this. What is the length of the leftmost derivation for the correct string above? What is the length of the leftmost derivation? Length of leftmost derivation for the correct string above. This is the linked question. Correct string above. So here options given are A4, B5, C6, D7. So we need to find out correct string is already we know, that is AA, BB, CC, DD. So for this, the length of leftmost derivation I have to find out. I will write here. So leftmost derivation means the productions are to be applied from the leftmost variable onwards. So that it will be S2. We have to use ASD. Again one more A is required. That's why S is replaced with AAD. I will stop S and D's. Again A is replaced with, leftmost variable is A. It will replaced with BAC. DD will be continued. And A is leftmost. That can be replaced with BC. So how many productions are applied? 1, 2, 3, 4. So length of leftmost derivation is 4. Option A is the correct option here.